The logarithmic function. Hello everyone, let's begin our lesson on the logarithmic function. To start, let's look back at what we have already covered. In our previous subsections, we explored the exponential function. As you recall, an exponential function is one where we take a fixed base and raise it to a variable power to determine a final value. Now, in this subsection, we are going to introduce the logarithmic function. The most important thing to understand right away is that the logarithmic function is essentially the inverse, or the reverse operation, of the exponential function. While the exponential function focuses on the result of the power, the logarithm allows us to work backward. In the next few slides, we will dive deeper into how this inverse relationship works and how to apply it. Understanding the concept of an inverse. Now that we have introduced the topic, let's dive deeper into the logic behind it. To truly grasp how logarithms work, we must first understand the fundamental concept of an inverse function. Think of it as a reversal of roles. If an exponential function asks the question, what is the result when I raise base b to the power of x? Then the logarithmic function asks the exact opposite. To what power must I raise base b to obtain the result a? Let's look at a concrete example to make this clearer. We already know from our previous studies that 2 raised to the power of 3 equals 8. If we were to express this statement in logarithmic form, we are essentially asking the question, to what power must 2 be raised to get 8? The answer, of course, is 3. By focusing on the exponent rather than the result, we are performing a logarithmic operation. This conceptual shift prepares us for the formal mathematical definition we will see in the next slide. Formal definition. Now that we have established the conceptual idea of the inverse in the previous slide, let us move on to the formal mathematical definition of the logarithmic function. Starting with the notation, for any real number b and a positive real number a, the logarithm of a to the base b is written as log base b of a. To put this into a precise equation, we define the value x as equal to log base b of a if, and only if, b raised to the power of x equals a. This is the mathematical way of stating the reverse relationship we discussed earlier. It tells us that the logarithm is simply the exponent we need to apply to the base to reach our target number. Let us break down the specific components of this notation so there is no confusion. First, we have b, which is the base of the logarithm. For the function to be well defined, the base must be greater than 0 and it cannot be equal to 1. Next, we have a, which is known as the argument. This is the number we are taking the logarithm of. It is critical to remember that the argument must always be a positive number, meaning it must be greater than 0. Finally, we have x, which is the exponent or the resulting value of the logarithm. Understanding these 3 components is essential, as they form the foundation for treating the logarithm as a mathematical function, which we will examine in the next slide. The logarithm as a function. Now that we have established the formal definition of a logarithm, let us look at it through the lens of a mathematical function. When we treat the logarithm as a function, we are essentially describing a mapping from the set of positive real numbers to the set of all real numbers. To put this into mathematical notation, we write log base b mapping from r plus to r. Let me break down what this notation actually means for you. First, let's discuss the domain. The domain refers to the possible inputs, which we call x in this case. X must belong to the set of positive real numbers. This is a critical point to remember. You cannot take the logarithm of 0 or any negative number. If you try to do so, the expression becomes undefined. Next, we have the range. The range refers to the possible outputs, which we call y. Unlike the domain, the range consists of all real numbers. This means the result of a logarithmic function can be a negative number, 0, or a positive number. Finally, let's reinforce the functional relationship we discussed in the previous slides. We can state that y equals log base b of x if, and only if, b raised to the power of y equals x. This simply confirms that the logarithmic function is the inverse of the exponential function, a concept we will apply in the upcoming examples and real-world applications. Real-world application, the Richter scale. Now that we have established the formal definition and the functional properties of logarithms, let's look at how these concepts are applied in the real world. You will find that logarithms are essential in science for measuring phenomena that grow exponentially, as they allow us to represent very large ranges of values in a more manageable way. A prime example of this is the Richter scale, which is used to measure the magnitude of earthquakes. The magnitude, denoted by the letter m, is defined using a base 10 logarithm. The formula is written as m equals log base 10 of the quantity a divided by a 0. To clarify the terms in this formula, a represents the measured amplitude of the seismic wave, while a 0 represents a standard reference amplitude. Because this is a logarithmic scale, the numbers do not increase linearly. Instead, an increase of 1 unit on the Richter scale, for example, moving from a magnitude 5 to a magnitude 6, actually represents a 10-fold increase in the amplitude of the earthquake's wave. This illustrates the power of the logarithmic function in simplifying massive scales. Now that we understand the conceptual application, let's move forward and practice the mechanical skill of converting between exponential and logarithmic forms. Step-by-step examples, converting forms. Now that we have established the formal definition and the functional properties of logarithms, it is crucial that you become proficient in switching between the exponential form and the logarithmic form. This skill is the foundation for solving more complex logarithmic equations, which we will encounter later. Let us begin with example 1, where we convert an exponential expression into a logarithmic one. Suppose we have the equation 5 squared equals 25. To rewrite this, we follow a systematic 4-step process. First, identify the base. In this case, the base is 5. Second, identify the exponent, which is 2. Third, identify the result of the operation, which is 25. Finally, we apply the definition we discussed in the previous slides. Log base b of a equals x. By plugging in our values, we get the result. Log base 5 of 25 equals 2. Now, let us look at example 2, which is the reverse process, converting a logarithmic form back into an exponential form. Consider the statement, log base 3 of 81 equals 4. Again, we follow a step-by-step approach. First, identify the base of the logarithm, which is 3. Second, identify the logarithm value, which represents our exponent. Here, that value is 4. Third, identify the argument, which is 81. Finally, we apply the exponential definition. Base b raised to the power of x equals a. This gives us the result, 3 to the power of 4 equals 81. Mastering these conversions is essential, as it allows you to move fluidly between these two mathematical perspectives. In the next slide, we will summarize the key takeaways to ensure these concepts are firmly rooted before we discuss common pitfalls to avoid. Key takeaways. Now that we have worked through the practical examples of converting between forms, let us summarize the key takeaways to ensure you have a solid foundation. First, always remember that the logarithmic function is the inverse of the exponential function. As we discussed at the beginning of this lesson, this means they are essentially opposite operations that undo one another. Because of this relationship, the statement log base b of a equals x is mathematically equivalent to saying b raised to the power of x equals a. This equivalence is the core principle we used in our previous examples to switch between logarithmic and exponential forms. Next, let us revisit the constraints of the function. The domain of log base b of x is 0 to infinity. In plain language, this means that the input, or the argument x, must always be a positive number. Finally, regarding the output, the range of log base b of x is negative infinity to positive infinity. This indicates that the resulting value of a logarithm can be any real number, whether it is negative, 0, or positive. Keep these fundamental rules in mind, as they will be essential for avoiding the common mistakes we will cover in the final slide. Common mistakes to avoid. Now that we have covered the definitions and examples, let's wrap up by discussing some common pitfalls to ensure you avoid these mistakes in your assignments and exams. First, be very careful about taking logarithms of non-positive numbers. A frequent error is attempting to calculate the logarithm base b of 0 or the logarithm base b of -5. As we discussed when talking about the domain of the function, the argument, which is the number we are taking the logarithm of, must always be greater than 0. This is because there is no possible power to which you can raise a positive base b to produce a result that is 0 or negative. Second, avoid confusing the base with the argument. It is quite common for students to accidentally swap these two values. To keep them straight, always remember the principle we used in our conversion examples. The base of the exponent is the exact same value as the base of the logarithm. In the exponential equation b to the power of x equals the value b serves as the base for both the power and the log. Finally, do not assume that the notation for a logarithm is a multiplier. When you see log base b of a, remember that this is a single functional notation. It does not mean the word log multiplied by b multiplied by a instead. It is a specific mathematical operation that asks a specific question about exponents.